The ocean covers more than 361 million square kilometers, which is about 139 million square miles. Most of it lies beyond sunlight. Most of it has never been seen by human eyes. Even today, we have visually explored less than 0.001% of the deep ocean floor. That is an area roughly the size of Rhode Island, compared with the wilderness that covers nearly two-thirds of our planet. Somewhere within that darkness lived one of the largest predators the Earth has ever produced. For nearly 20 million years, Megalodon dominated the world's oceans. It outlasted countless marine species, survived enormous shifts in climate, and left behind thousands of fossil teeth scattered across every ocean basin. Science says its story ended 3.6 million years ago, yet some discoveries have refused to fit comfortably within that conclusion. In 1875, an expedition aboard HMS Challenger recovered megalodon teeth from nearly 14,000 feet below the Pacific Ocean. Decades later, one researcher argued they were only around 11,000 years old, placing them thousands of years closer to the present than anyone expected. Far below the surface, unexplained bite marks have also appeared on deep-sea communication cables, at depths where very few large predators have ever been directly observed. And every time we have sent cameras into parts of the deep ocean that had never been explored before, we have encountered animals that science did not know were there. None of these observations prove that Megalodon survived, but neither have they disappeared from scientific discussion entirely. When so little of the deep ocean has ever been seen, the line between extinction and absence becomes more complicated than it first appears. Before we continue, let me know in the comments if you have any topic suggestions you would like me to cover in future videos. Now, let's leave the shoreline behind and descend into the deep ocean, where the evidence becomes far more difficult to dismiss. Long before the name Megalodon appeared in the fossil record, another story had already been unfolding beneath ancient seas for almost 105 million years. It was not the history of a single predator, but of an enduring bloodline that survived shifting continents, changing oceans, and one of the greatest catastrophes life has ever endured. Generation after generation, this dynasty adapted without interruption, each descendant carrying subtle changes that slowly reshaped one of the longest successful lineages among large marine hunters. The earliest confirmed ancestor known from this remarkable family is Cretolumna, a shark that lived during the age of the dinosaurs more than 105 million years ago. It hunted through oceans that looked profoundly different from those of today, then endured the immense upheaval caused by the asteroid impact that brought the Cretaceous-Paleogene extinction to the world. Countless creatures vanished during that event, yet this lineage continued. It crossed the boundary between lost worlds and living ones, becoming part of a new ocean where opportunity waited among recovering ecosystems. From that resilient foundation emerged Otodus obliquus, widely recognized as the first unmistakable ancestor of the later giants. Appearing roughly between 60 million and 45 million years ago, this shark already reached about 10 meters, which is about 33 feet in length. Its broad body and formidable jaws hinted at a future still unfolding across immense spans of geological time. It occupied oceans during the Paleocene and Eocene epochs, when marine mammals had only begun their own evolutionary journey, and the balance of ocean life remained very different from the familiar seas of the present. Evolution rarely moves through sudden leaps. Instead, it proceeds by countless small adjustments, accumulating across immense stretches of time. Otodus auriculatus followed, displaying larger teeth and greater body size. After it came Otodus angustidens, Pushing those trends even farther, each successor became more capable, more imposing, and better suited to dominating warm marine environments. The pattern resembles the slow turning of a vast wheel rather than a sequence of dramatic transformations. Over millions upon millions of years, natural selection refined a predator already standing near the summit of its world. Around 23 million years ago, during the early Miocene, that gradual progression reached its most extraordinary expression with the emergence of Otodus Megalodon. Popular imagination often places it beside the modern great white shark, as though one simply grew into the other. The fossil evidence tells a different story. Megalodon belonged to the extinct family Odontidae, while the great white belongs to a separate branch more closely related to the mako shark. Their resemblance arose independently through convergent evolution, with both developing broad, triangular, serrated teeth, because similar ecological pressures favored similar solutions. For well over a century, those striking teeth encouraged scientists to group them together before deeper anatomical study revealed their separate histories. Once established, Megalodon remained the undisputed apex predator of warm oceans for nearly 20 million years, a reign extending longer than the entire evolutionary history of true whales. During that immense interval, its presence stretched across almost every suitable sea on Earth. Fossils have been recovered from Maryland, Panama, the Canary Islands, Japan, Australia, Peru, Florida, and South Africa, with every continent except Antarctica preserving evidence of its existence. Those scattered teeth are more than isolated relics. Together they map an empire measured not by borders, but by oceans themselves. Seen in that light, Megalodon becomes something far greater than an unusually large shark. It represents the final achievement of a dynasty that endured for over 100 million years, surviving extinction, reshaping itself across changing ages, and ultimately producing the most dominant large predator the ocean has ever known. Its story begins long before its famous name, rooted in a lineage whose persistence alone remains one of evolution's most remarkable accomplishments. Scale is easy to imagine until it reaches the point where imagination begins to lose its grip. Megalodon has occupied that boundary for more than a century, not because its existence is uncertain, but because every new discovery has changed the dimensions of the animal itself. With no complete skeleton preserved, each generation of paleontologists has rebuilt its form from scattered clues, allowing the picture to sharpen little by little across decades of patient study. The most recent reconstruction, published during 2025 by a collaboration of 29 fossil shark specialists, places the greatest known individuals at approximately 24.3 meters, which is about 79.7 feet in length. Rounded for everyday comparison, that is about 80 feet. That is nearly 24 meters. Even this measurement represents an informed estimate rather than an absolute limit, assembled from fossil teeth, preserved vertebrae, living shark anatomy, and the mathematical relationships that connect them. Every refinement has brought the animal into clearer focus while reminding researchers how much of its body has vanished forever. Length alone, however, only hints at the presence such a creature would have carried through the sea. A detailed three-dimensional biomechanical model published during 2022 estimated that an adult megalodon possessed enough biting capacity to consume an entire killer whale in roughly 5 bites. Those calculations were based not on fantasy, but on reconstructed jaw mechanics, estimated muscle mass, and the known proportions of modern sharks. The result describes a predator whose feeding ability was shaped as much by efficiency as by overwhelming size. Its jaws opened to nearly 3 meters, that is nearly 10 feet, across at their widest extent, creating an opening broad enough to engulf a small automobile. Within those jaws rested rows of triangular teeth reaching approximately 18 centimeters in length. Their finely serrated edges were specialized for slicing through blubber, dense muscle, and heavy bone with remarkable effectiveness. Like modern sharks, Megalodon continually replaced lost teeth throughout its life. Each individual tooth eventually fell away, only to be followed by another waiting directly behind it, creating an endless cycle of renewal that left thousands of fossilized reminders scattered across ancient seabeds. Estimating the animal's total mass has proven even more challenging than estimating its length. Depending upon the body proportions selected for each reconstruction, scientific estimates range from roughly 50 to more than 100 metric tons. Such differences reveal less about uncertainty in the fossil evidence than about uncertainty in body shape itself. For many decades, artists and scientists alike pictured Megalodon as an enormous version of the modern great white shark, broad through the body and immensely powerful. That familiar image became deeply rooted in popular culture, appearing in books, museums, documentaries, and films. Recent research has gently shifted that vision in another direction. A comprehensive study published during 2025, led by DePaul University paleobiologist Kenshu Shimada, together with 28 fellow researchers, concluded that Megalodon's proportions were likely closer to those of the modern lemon shark. Instead of an extremely stocky hunter, the evidence points toward a longer, more streamlined body designed for hydrodynamic efficiency. Physics offers a compelling explanation. As animals become larger, broad body shapes create increasing resistance while moving through water. The great white shark appears to reach a practical upper limit at around 7 meters, which is about 23 feet, whereas a more slender design could continue scaling upward without the same energetic penalty. That revised form also changes how the animal likely moved. Scale-based analyses suggest a steady cruising speed between about 1.3 and 2.2 miles per hour. Rather than an endlessly charging giant, Megalodon may have spent much of its life traveling with measured efficiency across immense distances, conserving energy until brief bursts of acceleration carried it toward prey. Almost everything known about this extraordinary body emerges from fossil teeth, a handful of preserved vertebrae, and careful comparison with living relatives, because the cartilaginous skeleton that once supported the largest shark ever known disappeared long before stone could preserve its shape. Some discoveries do not add another detail to an animal already known. They transform the animal entirely. For more than a century, Megalodon had been imagined as an immense version of the typical shark, its body assumed to rise and fall with the temperature of the surrounding sea, conserving energy in the familiar way shared by most of its living relatives. That assumption endured because no direct evidence existed to challenge it. The fossil record preserved teeth in extraordinary abundance, yet it revealed almost nothing about the living chemistry that once animated the body behind them. That changed during the month of June in the year 2023, when a peer-reviewed study published in the Proceedings of the National Academy of Sciences offered the first direct evidence that Megalodon belonged to a very different biological category. Led by Michael Griffiths and Martin Becker of William Patterson University, together with researchers from the University of California, Los Angeles, and the University of California, Merced, the team turned not to speculation, but to microscopic chemical signatures preserved within fossilized teeth. They combined clumped isotope paleothermometry with phosphate oxygen isotope analysis, techniques capable of preserving a remarkable record of the temperatures under which those ancient tissues originally formed. The results pointed toward a striking conclusion. Megalodon maintained a body temperature approximately 7 degrees Celsius or 45 degrees Fahrenheit, warmer than the surrounding seawater. This pattern matches a condition known as regional endothermy, the same thermal strategy used by living mako sharks and great white sharks, in which certain regions of the body remain substantially warmer than the environment. Until this study, such warmth had been inferred for extinct megatooth sharks only through indirect reasoning. Here, for the first time, the evidence came directly from the chemistry locked inside the fossil itself. That warmth reshapes nearly every aspect of the animal's life. Muscles supplied with elevated temperatures contract more efficiently, allowing stronger and more sustained movement through cooler water. Nerve signals travel with greater speed, sharpening sensory performance during pursuit. Digestion proceeds more rapidly, converting prey into usable energy with greater consistency. Instead of depending upon external warmth before reaching peak performance, Megalodon likely carried much of its own thermal advantage wherever it traveled. Oceans that cooled with depth or changing seasons would not immediately slow a predator capable of generating its own internal heat. Such advantages, however, were never free. Every degree maintained above the surrounding sea demanded additional energy. Every hour of movement required a constant supply of food, and every day imposed an immense metabolic cost. A cold-blooded shark can endure extended periods with relatively little nourishment because its body conserves energy. A warm-bodied predator cannot rely upon the same economy. Its biological engine continues working without pause, consuming fuel even during periods of rest. The larger the body became, the greater that demand would have grown. The researchers proposed that this remarkable metabolism may also explain how Megalodon achieved such extraordinary dimensions. A body capable of producing and retaining heat could support stronger muscles, longer migrations, and greater hunting performance, creating a reinforcing cycle in which increased metabolic capacity encouraged increased body size. Gigantism, in this view, was not merely a consequence of abundant prey. It may have been woven directly into the animal's physiology from the beginning. Yet the same adaptation carried another consequence, one that reaches beyond success into vulnerability. The study notes that the energetic burden imposed by regional endothermy may ultimately have contributed to Megalodon's disappearance. A predator requiring vast and uninterrupted nourishment would become increasingly dependent upon stable marine ecosystems capable of sustaining that appetite across immense spans of time. What once elevated the lineage above every rival may also have narrowed the margin within which it could survive. The image that emerges is no longer that of a sluggish giant drifting through ancient seas, but of a warm-bodied predator operating close to the biological limits that the ocean itself could sustain. Every living creature carries an invisible arithmetic within its body. For Megalodon, that arithmetic was immense. Researchers estimate that a fully grown individual required approximately 100,000 kilocalories every single day simply to maintain the powerful metabolism that recent discoveries have revealed. That requirement was not an occasional burden, but a continuous biological obligation, shaping every movement, every migration, and every choice the animal made across the ancient seas. Its relationship with the ocean was therefore defined not only by strength, but by an endless search for enough energy to keep an extraordinary body alive. The richest source of that energy came from marine mammals. Fossil evidence recovered from multiple ocean basins preserves ribs, vertebrae, and other whale bones bearing broad serrated bite marks whose size and geometry closely match the teeth of Megalodon. Dolphins, porpoises, and a wide variety of early whales formed the foundation of its diet. These encounters were not isolated accidents preserved by unusual conditions. They appear repeatedly across distant fossil deposits, revealing a predator that interacted with cetaceans wherever their ranges overlapped throughout millions of years. Chemical evidence tells a similar story from another direction. Nitrogen isotope analysis places Megalodon at least 2 complete trophic levels above the modern great white shark. Rather than sharing the same position in the food web, Megalodon occupied a level beyond it, feeding upon animals that were themselves major predators or large consumers. It did not simply replace the ecological role held by today's great white. It operated above that familiar hierarchy, occupying a position that has no direct equivalent in the modern ocean. Even so, its feeding behavior appears to have been more flexible than once believed. Zinc isotope research, published during 2022, demonstrated that Megalodon was not exclusively dependent upon whales. Instead, it behaved as an opportunistic supercarnivore, adjusting its prey according to whatever large animals were most abundant within a particular region. This flexibility likely increased its resilience across changing environments and allowed populations to thrive over an immense geographical range rather than depending upon a single source of food. Life began in a very different setting from the open sea, ruled by adults. Juvenile megalodons occupied sheltered coastal nurseries, protected bays, and broad estuaries where fish and smaller marine mammals were plentiful while larger predators were less common. Fossil teeth belonging to young individuals have been discovered at nursery sites in Panama, Maryland, the Canary Islands, and Florida, suggesting that these protected waters serve the same essential purpose across much of the species' range. At birth, an infant megalodon already measured approximately 3.5 meters, which is about 11.5 feet, making it larger than many fully grown shark species alive today. As those young sharks matured, their lives changed dramatically. They gradually left the safety of coastal waters and entered the open ocean, where increasingly large cetaceans became their principal prey. During the early Miocene, this transition unfolded within an ocean, experiencing an extraordinary flourishing of whale diversity. Small and medium-sized whales were abundant across warm seas, providing an exceptionally rich source of nourishment for a predator whose appetite demanded nothing less than abundance on a continental scale. One remarkable fossil captures this progression with striking clarity. The rib of a baleen whale preserves 3 distinct tooth marks left by a juvenile megalodon estimated to have measured between 4 meters, which is about 13 feet, and 7 meters, which is about 23 feet in length. Even before reaching adulthood, the young shark was already attacking prey larger than itself, demonstrating hunting behavior that anticipated the ecological role it would eventually dominate. Across nearly 20 million years, those countless hunts shaped far more than the fate of individual animals. By consuming large marine mammals generation after generation, Megalodon influenced whale populations, altered predator and prey relationships, and helped regulate the structure of ancient ocean food webs. The echoes of that long influence remain woven into modern marine ecology, preserved not through living encounters, but through the fossil record left behind by one of the greatest feeding machines the ocean has ever produced. Every predator is shaped as much by its surroundings as by its own anatomy. Teeth, muscles, and instinct matter greatly, yet they can only flourish in a world capable of sustaining them. The seas that nourished Megalodon were not simply earlier versions of the oceans that exist today. They belonged to a different chapter in Earth's history, one in which climate, coastlines, and marine life aligned to support a hunter of extraordinary scale. During the Miocene, the planet was generally warmer than it is today. Sea surface temperatures across many regions remained several degrees higher, creating vast expanses of productive tropical and subtropical waters. Broad continental shelves stretched along coastlines, forming extensive shallow marine environments rich with fish, marine mammals, and countless smaller organisms supporting the food web below them. These productive margins became both feeding grounds for adults and sheltered nurseries where the next generation could begin life under favorable conditions. At the same time, whales were experiencing one of the greatest periods of diversification in their evolutionary history. Small and medium-sized cetaceans occupied nearly every suitable marine habitat, filling ecological roles that ranged from filter feeders to swift predators. Among the most formidable were the macroraptorial sperm whales, including the remarkable Zygophysiter, powerful hunters equipped with large interlocking teeth designed for seizing substantial prey. Fossil evidence and trophic analysis suggest that even these imposing marine predators may themselves have fallen within Megalodon's hunting range, illustrating how completely it occupied the highest level of the ancient ocean food web. Yet even prosperous ecosystems carry the seeds of future change. By around 11 million years ago, the diversity and abundance of these predatory sperm whales began to decline. Their disappearance did not immediately threaten Megalodon, whose diet remained broad and adaptable, but it marked one of the earliest signs that the marine communities supporting the giant predator were beginning to reorganize. The balance that had endured for millions of years was becoming gradually less stable. Far greater changes arrived through the slow movement of continents. Around 3 million years ago, the Panama Seaway closed as land rose between North and South America. This geological transformation redirected major ocean currents linking the Atlantic and Pacific Oceans, altering the circulation of heat across the planet. Water that had once flowed freely between the two great basins followed entirely new pathways, changing regional climates, nutrient distribution, and patterns of marine productivity over immense distances. Those changes reached far beyond the surface. Warm coastal habitats gradually contracted as global circulation shifted and climates continued cooling. The shallow environments that had supported dense concentrations of marine life became less extensive in many regions, reducing the availability of both productive hunting grounds and protected nursery areas. For an animal whose entire life cycle depended upon these environments, such transformations accumulated into increasingly serious ecological pressures. The whales changed alongside the water that sustained them. During the Pliocene, many of the smaller and medium-sized cetaceans that had once flourished began declining in both abundance and diversity. Since these species formed the principal food source for Megalodon, every reduction echoed upward through the food web. A predator requiring enormous quantities of nourishment could tolerate occasional fluctuations, but long-lasting reductions across multiple ocean basins gradually reshaped the energetic landscape on which its survival depended. These changes formed part of a broader biological transition recognized in the fossil record as the Pliocene marine megafauna extinction event. Numerous large marine animals declined or disappeared during this interval, revealing that Megalodon was not facing an isolated crisis. Entire communities of large-bodied species were responding to the same combination of climatic change, altered ocean circulation, and shifting ecological relationships. Seen together, these events reveal a pattern unfolding across millions of years, rather than a sudden collapse. The ancient ocean that had sustained Megalodon through countless generations was gradually becoming a different place, with different currents, different coastlines, and different communities of prey. Long before the giant shark vanished from the fossil record, the remarkable world that had allowed such a predator to thrive had already begun to fade, carrying with it the conditions upon which its long reign had always depended. Extinction rarely arrives as a single dramatic moment. More often, it begins with subtle changes that spread across an ecosystem until every familiar pattern has shifted. Around 3.5 million years ago, the Earth entered one of those turning points. The Pliocene cooling event gathered strength across the planet, bringing accelerating changes to ocean temperatures, sea levels, and the circulation of entire marine basins. The world that had sustained Megalodon for millions of years began changing faster than the giant predator could easily follow. As polar ice sheets expanded, enormous volumes of water became locked within growing masses of ice. Global sea levels fell, exposing broad stretches of continental shelf that had once rested beneath shallow seas. Those flooded coastal plains had provided far more than productive feeding grounds. They were also the protected nursery environments where young megalodons spent the earliest stages of life. As those habitats diminished, each generation faced fewer places where newborn sharks could grow with relative safety before entering the open ocean. Cooling spread through the seas themselves. Regions that had long remained comfortably within the preferred thermal range of a warm-bodied predator gradually became less suitable. Although Megalodon possessed the remarkable ability to maintain body temperatures approximately 7 degrees Celsius or 45 degrees Fahrenheit above the surrounding water, that adaptation could not erase the energetic cost imposed by an increasingly colder ocean. Every migration demanded more energy, every hunt required greater efficiency, and every successful meal became more important than the one before. Many prey species responded to these changing conditions by shifting their ranges toward higher latitudes, following productive waters that remained favorable for survival. For Megalodon, this movement created a profound biological dilemma. The whales and other marine mammals that had supported its immense metabolism increasingly occupied environments where prolonged hunting became progressively more difficult. A predator adapted to warm marine ecosystems could not simply abandon its physiology and pursue prey indefinitely into colder seas. The arithmetic of survival therefore became increasingly unforgiving. A body requiring approximately 100,000 kilocalories each day cannot simply accept less nourishment when food becomes scarce. The demand remains constant even as opportunity declines. Every reduction in available prey echoed directly through the predator that depended upon it, narrowing the margin between successful survival and gradual starvation. What had once been an abundant ecological relationship slowly became an increasingly fragile balance. The youngest members of the species faced an equally serious challenge. As coastal nursery habitats contracted, the fish, smaller marine mammals, and protected waters that had sustained juvenile megalodons also diminished. Without extensive nursery grounds, successful recruitment into the adult population inevitably declined. Even healthy adults cannot preserve a species indefinitely if each new generation becomes progressively smaller than the one before. The roots supporting the population had begun disappearing beneath the changing shoreline. These pressures extended throughout the marine food web. Ocean productivity declined across many regions as changing circulation altered nutrient distribution. Reduced productivity meant fewer phytoplankton, fewer small fish feeding upon them, fewer medium-sized predators, and ultimately fewer marine mammals at the highest levels of the ecosystem. Each layer depended upon the one beneath it, and disturbances near the foundation eventually reached the largest hunter of them all. The fossil record preserves an especially compelling detail within this long transformation. Megalodon's disappearance does not occur long before this climatic transition, nor long after it. Instead, its final confirmed appearances coincide with the most intense phase of Pliocene cooling. The timing aligns so closely that the relationship is difficult to dismiss as coincidence alone. Rather than pointing toward a sudden catastrophe, the evidence describes an ecological cascade unfolding across interconnected systems. Even then, the end was probably not simultaneous everywhere. Fossil discoveries from the Pacific suggest that some regional populations endured longer within warmer latitudes where favorable conditions persisted after they had vanished elsewhere. One refuge after another gradually disappeared until the remaining pockets of suitable habitat finally contracted beyond recovery. The collapse, viewed through the deep perspective of geological time, resembles a tide slowly withdrawing from a shoreline, leaving less space with every passing age until nothing remained for the great predator that had once ruled those ancient seas. Not every rival defeats another through greater strength. Sometimes survival belongs to the animal whose needs are simply smaller. As the oceans continued changing, another shark was expanding across marine ecosystems, one whose appearance in the fossil record arrived at a remarkably significant moment. Around 5 million years ago, the modern great white shark emerged as an increasingly important ecological presence, just before Megalodon's own record began drawing toward its final, confirmed chapter. That sequence of events has encouraged many researchers to examine whether the two predators shared more than the same oceans. The idea is neither sensational nor universally accepted. It remains an active scientific hypothesis built upon ecological evidence rather than direct observation. If two large predators pursue similar prey while living in increasingly constrained environments, competition becomes a possibility worth investigating, even when the larger animal appears overwhelmingly dominant. One important clue comes from zinc isotope analysis. During the early Pliocene, chemical evidence preserved within megalodon teeth suggests that populations in the Atlantic occupied a slightly lower trophic position than earlier members of the species. Rather than feeding consistently upon the largest available marine mammals, they appear to have relied more frequently on prey lower within the food web. Such a shift does not necessarily indicate weakness. Instead, it may reflect an ecosystem where preferred prey had become less abundant, encouraging a predator once accustomed to exceptional abundance to become increasingly flexible in its diet. The modern great white occupied many of the same ecological spaces. Both sharks hunted marine mammals. Both relied heavily upon productive coastal environments during important stages of their lives. Both required substantial prey capable of sustaining large bodies built for active hunting. As environmental changes reduced the richness of those habitats, the likelihood of overlapping resource use naturally increased. Even without direct confrontation, two predators can influence one another simply by pursuing the same limited supply of food. One crucial difference separated them. The great white remained primarily cold-blooded, allowing it to survive with a considerably lower metabolic demand. Although it possesses specialized adaptations that warm certain body regions, its overall energetic requirements remain far below those of a giant predator maintaining elevated body temperatures across an immense body. This difference meant the great white could persist on smaller meals, tolerate colder waters more comfortably, and exploit prey that would have provided too little nourishment for a fully grown megalodon. In a changing ocean, efficiency can become as valuable as sheer size. Research published during 2022 strengthen this possibility through additional isotopic evidence showing substantial overlap between the diets of the two species. Where marine mammal populations remained abundant, such overlap may have mattered little. During periods of ecological decline, however, even moderate competition could become increasingly significant. Every seal, dolphin, or young whale consumed by one predator became unavailable to the other, gradually increasing pressure throughout an ecosystem already under strain. Some researchers therefore propose that expanding great white populations captured ecological opportunities that Megalodon gradually lost. As cooling waters altered marine habitats, the smaller shark could continue hunting successfully across thermal conditions that demanded ever greater energy from its larger relative. Access to colder environments effectively widened the great white's hunting grounds, while narrowing those available to Megalodon. The balance shifted not because one predator suddenly became stronger, but because one remained more adaptable as circumstances changed. Scientific caution remains essential. Many paleontologists argue that the immense difference in body size limited direct competition, since adult megalodons targeted prey considerably larger than those most commonly hunted by great whites. Others suggest that dietary overlap varied between regions and across different stages of environmental change. The available evidence supports the possibility of competition without establishing it as the decisive explanation for extinction. Viewed within the broader pattern already unfolding across the late history of Megalodon, the great white factor appears less like a single cause and more like another weight added to an already burdened system. Shrinking nursery habitats, declining prey, changing ocean circulation, increasing energetic costs, and growing ecological overlap all converged upon a predator whose remarkable success had always depended upon extraordinary abundance. Competition, if it played a meaningful role at all, was likely one thread woven into a much larger tapestry of environmental transformation, rather than the solitary force that brought an ancient dynasty to its end. Among all the evidence gathered across generations of research, one line of reasoning stands above the rest because it depends upon something sharks have always done. A shark does not keep the same teeth throughout its life. Each tooth eventually falls away, and another moves forward to replace it. This process repeats continuously from youth until death, leaving behind a steady trail of durable fossils. For Megalodon, whose existence stretched across nearly 20 million years, that simple biological habit produced an archive unlike almost anything else in the natural world. The number of teeth generated by a species over such an immense span of time is almost beyond imagination. Individual sharks replaced teeth again and again throughout their lives, while countless generations followed across millions of years. As those teeth settled into marine sediment, they accumulated across ocean basins on a global scale. Today, fossil deposits from many parts of the world preserve this extraordinary record, offering paleontologists a remarkably consistent window into the history of one of the greatest predators that ever lived. Within that vast archive, one observation carries exceptional weight. No confirmed megalodon tooth, younger than approximately 3.6 million years, has ever been verified from any ocean on Earth. Thousands upon thousands of specimens have been recovered, examined, compared, and dated, yet none has crossed that boundary under reliable scientific scrutiny. The absence is striking precisely because the record before that point is so abundant. For this reason, many paleontologists regard the teeth as the strongest single argument supporting extinction. If Megalodon still inhabited the oceans today, it would continue shedding teeth exactly as its ancestors always had. Those fresh teeth would settle onto the seafloor, become incorporated into marine sediments, and eventually appear through dredging operations, scientific trawls, coastal erosion, or natural deposition along beaches. The expectation follows directly from shark biology rather than speculation, making the absence of modern teeth especially persuasive. Color provides another important clue. Fossilized megalodon teeth are commonly dark brown, gray, or black because minerals gradually replaced or stained their original composition during millions of years buried within sediment. Their appearance reflects geological history as much as biological origin. A recently shed megalodon tooth, by contrast, would remain white, displaying the fresh enamel expected from a living shark. Despite decades of searching by scientists and fossil collectors alike, no white megalodon tooth with a verified age younger than the Pliocene has ever been confirmed through careful examination. The evidence extends beyond teeth alone. A predator measuring more than 24 meters, which is about 79 feet, would leave unmistakable traces upon the marine mammals it hunted. Modern whale carcasses recovered from oceans around the world are routinely examined for injuries caused by predators, scavengers, collisions, and disease. Yet none has displayed bite marks, whose spacing, jaw geometry, or serrated tooth impressions correspond convincingly to Megalodon. Such encounters would be expected if a population of giant sharks still occupied the same waters as modern whales. Other forms of evidence have also remained absent. Commercial fishing has captured enormous numbers of marine animals across the world's oceans without accidentally recovering a living megalodon. Deep water exploration has expanded dramatically through remotely operated vehicles, research expeditions, and improved imaging technology, yet no verified footage has emerged. Sonar surveys have recorded countless underwater targets, but none has produced evidence accepted by specialists as belonging to this extinct shark. Taken together, these independent observations have produced an unusually strong scientific consensus. Paleontologists, marine biologists, and shark specialists overwhelmingly conclude that Megalodon is extinct because multiple lines of evidence converge upon the same conclusion. The fossil record, the absence of modern teeth, the lack of contemporary bite evidence, and the complete absence of verified physical encounters all reinforce one another. Any proposal that Megalodon survives into the present must therefore overcome this accumulated body of evidence, a standard that no surviving hypothesis has yet successfully met. Sometimes, a single pair of fossils can influence decades of debate, not because they overturn established science, but because they appear to do so. Such a moment began in the year 1875, when the research vessel, His Majesty's Ship Challenger, the expedition widely regarded as the beginning of modern oceanography, dredged the floor of the Pacific Ocean near Tahiti. From a depth of approximately 14,000 feet, which is about 4,267 meters, the expedition recovered the first known megalodon teeth ever brought up from the open deep ocean. They were cataloged alongside countless other discoveries and placed into museum collections, where they remained for many years without attracting unusual attention. For approximately 84 years, those remarkable teeth rested as scientific specimens rather than scientific mysteries. Their presence on the deep sea floor was noteworthy, but no accepted method existed for determining how long they had been lying there. The fossils became part of the growing archive assembled by generations of naturalists, waiting for new techniques that promised to read time from the minerals coating their surfaces. That opportunity appeared in the year 1959, when zoologist Vladimir Chernesky of Queen Mary College in London examined the Challenger specimens using manganese dioxide deposition rates. The method attempted to estimate age by measuring the thickness of mineral crust that had accumulated upon the fossil after it settled onto the ocean floor. If the growth rate of that crust could be estimated correctly, the age of the tooth might also be estimated. The results were astonishing. One tooth appeared to be approximately 24,000 years old. Another seemed to be only about 11,000 years old. Those estimates placed both specimens deep within human prehistory, millions of years younger than the accepted extinction of Megalodon. For advocates of surviving prehistoric animals, the findings became enormously influential. Although the broader scientific community remained unconvinced, the published claim spread widely and eventually became one of the foundational references within modern Megalodon survival literature. The difficulty lay not with the measurements themselves, but with the assumptions supporting them. Over the following decades, researchers demonstrated that manganese dioxide does not accumulate at a constant rate across the deep ocean. Deposition depends upon local chemistry, sedimentation, water movement, and numerous environmental variables that differ dramatically from one location to another. Chernesky had applied a growth rate that proved unsuitable for the Challenger site, causing the teeth to appear roughly 20 to 30 times younger than their true geological age. Additional investigation revealed another important characteristic of Megalodon teeth. Their dense construction allows them to resist physical and chemical deterioration exceptionally well. A tooth deposited during the Miocene can remain remarkably well preserved after millions of years resting upon the seafloor. An unexpectedly pristine appearance therefore says very little about when the tooth entered the sediment. Preservation reflects durability as much as age. The surrounding fossil assemblage strengthened that conclusion. Other shark teeth recovered from the same Challenger dredge included Carcharodon, Hastellus, and Parotidus benedenii, species securely assigned to the Miocene and Pliocene. Because these fossils were found together within the same geological context, they collectively indicate an ancient deposit rather than a mixture of recently shed remains. The Megalodon teeth belong to that same fossil community, not to a surviving modern population. A similar episode unfolded during the year 1988, when researchers applied the same manganese dating approach to Megalodon teeth recovered near Madagascar. Once again, the calculated ages ranged from approximately 15,000 to 60,000 years. Once again, later analysis demonstrated that the underlying assumptions about mineral accumulation were unreliable, and the apparent youth of the fossils dissolved under closer examination. Today, the Challenger teeth remain historically important, not because they challenge the extinction of Megalodon, but because they illustrate how science corrects itself. The fossils are millions of years old. The dating method proved unsuitable for the question being asked, and the extraordinary claim no longer stands. Yet the careful process of testing, questioning, and eventually overturning that conclusion offers a lasting example of how evidence becomes stronger through scrutiny rather than certainty. No archive is perfect, even one written across the floor of the sea. Every fossil rests within a landscape that continues to move long after the living creature has disappeared. Layers accumulate, currents wander, sediments shift, and the ocean continues shaping its own memory. The remarkable abundance of Megalodon teeth gives paleontologists extraordinary evidence. Yet understanding that evidence also requires understanding the nature of the archive itself. Because the seafloor preserves history with immense patience rather than flawless precision. The central assumption behind the fossil record is both sensible and largely reliable. A shark sheds its teeth throughout life. The teeth settle into sediment, and over immense spans of time, those sediments harden into the geological record. By comparing the age of surrounding deposits with the fossils they contain, researchers reconstruct vanished ecosystems with remarkable confidence. Most of the time, that approach works extraordinarily well, forming the foundation upon which much of paleontology has been built. Even so, the deep ocean is not completely motionless. Powerful bottom currents travel across abyssal plains, sweeping fine sediment from one location to another. Storm-driven events, submarine landslides, and changing circulation patterns can also disturb deposits that once appeared undisturbed. During these processes, fossils may be lifted, transported, and eventually settled again within younger or older sediment. A megalodon tooth deposited approximately 15 million years ago can therefore become physically incorporated into material of a different geological age without the tooth itself becoming younger. This process is neither speculative nor unusual. Paleontologists know it as reworking, a recognized taphonomic phenomenon documented throughout the fossil record. Reworking does not rewrite the age of a fossil. Instead, it alters the relationship between the fossil and the sediment immediately surrounding it. Because of that distinction, researchers examine not only individual specimens, but also the broader geological setting before drawing conclusions about age and origin. One instructive example comes from the Lomita Marl deposits of California. Megalodon teeth recovered there were initially presented as possible evidence that the species had survived much longer than expected. At first glance, the surrounding deposits appeared young enough to support that interpretation. More detailed stratigraphic investigation eventually revealed that mining operations had disturbed the site, physically mixing fossils from separate geological layers. The younger sediment had inherited much older teeth through human activity rather than natural survival, dissolving what had briefly seemed like an extraordinary discovery. The pace at which sediment accumulates introduces another layer of complexity. In some abyssal regions, new material settles upon the seafloor at rates measured in only a few millimeters per 1,000 years. Such remarkably slow accumulation means that objects separated by immense spans of time may appear surprisingly close together within the sediment column. A fossil can remain exposed upon the seabed for a very long interval before finally becoming buried beneath later deposits, complicating efforts to assign an exact depositional age based solely upon depth. These realities do not overturn the broader fossil record. Instead, they define its natural limits. The continued absence of convincingly young megalodon teeth across oceans worldwide remains powerful evidence that the species disappeared millions of years ago. Yet individual specimens must always be interpreted with care because reworking, disturbed deposits, and extremely slow sedimentation can occasionally create misleading geological associations. The uncertainty belongs to isolated fossils, not to the overall pattern established by thousands of discoveries. In that sense, the archive kept beneath the ocean is both dependable and imperfect. It preserves an immense history extending across millions of years while still carrying traces of the restless world that created it. The argument built from megalodon teeth, therefore, remains the strongest scientific case for extinction, not because every fossil speaks with complete certainty, but because countless independent discoveries, examined together across continents and ocean basins, continue telling the same enduring story with remarkable consistency. The map of the deep ocean appears complete only from a great distance. Blue fills the spaces between continents with reassuring simplicity, giving the impression that the planet beneath has already been explored. Yet that impression dissolves as soon as attention turns below the sunlit surface. The overwhelming majority of Earth's living space remains hidden beneath immense columns of water, where darkness, pressure, and distance combine to place much of the seafloor beyond direct human observation. A comprehensive study, published in the journal Science Advances, during the year 2024, gathered records from approximately 44,000 deep-sea expeditions conducted since the year 1958, across more than 120 countries. The conclusion was striking. Scientists have visually observed less than 0.001% of the deep ocean floor, an area roughly comparable to the state of Rhode Island, when measured against a realm that occupies approximately 361 million square kilometers, which is about 224 million miles. Beneath 200 meters, that is nearly 656 feet, the deep ocean contains more than 90% of the planet's marine volume, extending through approximately 1,335,000,000 cubic kilometers, that is nearly 320 million cubic miles, of water. The record of exploration is also uneven through time. Nearly 30% of all visual observations ever collected from the deep sea were made before the year 1980. Much of that pioneering work relied upon grainy black and white imagery, limited lighting, and equipment that revealed only small fragments of the surrounding landscape. Those expeditions transformed marine science, yet they also reflected the technological boundaries of their era, leaving countless details beyond the reach of the instruments available at the time. Geography introduces another limitation. Deep-sea exploration has been concentrated in only a handful of locations, where research institutions, funding, and logistical support have made repeated expeditions practical. Monterey Bay, the Hawaiian Islands, Suruga Bay, Sagami Bay, and waters surrounding New Zealand have received sustained attention across decades. Beyond those familiar regions stretches an immense expanse where no remotely operated vehicle has ever passed above the seafloor, and where no camera has recorded the landscape resting beneath. Life within that unseen realm remains equally uncertain. Marine biologists estimate that the ocean may contain between 700,000 and 1 million species. Roughly 2/3, and perhaps even more, have never been formally described. Every year, approximately 2,000 additional species enter scientific literature, each discovery reminding researchers that the catalog of marine life remains far from complete. Entire communities continue existing beyond observation simply because so little of their environment has ever been examined directly. These numbers reveal more than an ordinary gap in knowledge. They describe a frontier whose scale exceeds ordinary intuition. Human understanding of the deep ocean is built from scattered windows rather than continuous coverage. Each expedition contributes another fragment, yet the overwhelming majority of the abyss still lies beyond those isolated glimpses. The unknown is measured not by curiosity alone, but by the sheer dimensions of the environment itself. That perspective also shapes discussions surrounding extinction, demonstrating that a species is absent from an environment requires searching enough of that environment to justify the conclusion. Within coastal waters, heavily studied ecosystems, and commercially active regions, confidence can become very strong. Across the immense reaches of the abyss, however, direct observation remains remarkably limited. Scientific caution recognizes this distinction because absence of observation and observation of absence are related ideas, but they are not identical. None of this overturns the evidence presented by the fossil record. The continuing absence of convincing modern Megalodon remains a powerful conclusion supported by multiple independent lines of research. At the same time, the ocean itself reminds us that certainty grows from the quality and extent of observation. The deepest waters remain only lightly explored, preserving a world where discovery continues, where new species still emerge from darkness, and where the boundaries of knowledge are defined not by imagination, but by the extraordinary size of the sea itself. History has revealed an unexpected pattern beneath the sea. Every generation of explorers has believed the outlines of the deep were becoming familiar, only for the next expedition to return, carrying something that had never before entered scientific knowledge. These discoveries have not been limited to tiny organisms hidden beneath rocks or drifting through the darkness. Some have been large animals, powerful predators, and immense filter feeders whose existence remained concealed despite inhabiting a planet already covered by ships, satellites, and centuries of natural history. One remarkable example arrived through pure accident. During the year 1976, an anchor deployed by the United States Navy off the Hawaiian Islands became entangled with an unfamiliar shark. The animal proved to belong to an entirely unknown species, later named the megamouth shark. Growing to more than 5 meters, which is about 16 feet, this enormous filter feeder possessed a worldwide distribution while remaining completely beyond scientific awareness until that unexpected encounter. Even after its discovery, the species continued to resist observation. Across the decades that followed, fewer than 100 individuals were documented, despite the immense range they appear to occupy. Another inhabitant of the deep carried an even older story. The goblin shark represents a lineage extending back approximately 125 million years, preserving anatomical features that have changed remarkably little across immense spans of geological time. Because of this ancient ancestry, it is often described as a living fossil. Although specimens had occasionally reached the surface after accidental capture, observing the species within its natural environment remained beyond human experience. During the month of June, in the year 2026, researchers finally recorded living goblin sharks swimming freely in their home waters. One individual appeared near Jarvis Island in the central Pacific Ocean at a depth of approximately 2 kilometers, which is about 1.2 miles. Another was documented near the Tonga Trench. The species had never been absent. Human observation had simply not reached the places where it lived. The frilled shark offers another reminder of the same lesson. Its long body resembles an eel more than the familiar outline of modern sharks, while its mouth contains roughly 300 slender teeth arranged to seize soft-bodied prey. Descended from a lineage that has endured for approximately 80 million years, it remained so rarely encountered that many naturalists during the 19th century knew it only from damaged specimens brought accidentally to the surface. Its appearance seemed almost mythical until repeated observations gradually confirmed its place within the deep ocean ecosystem. An equally striking example emerged from the realm of the cephalopods. The colossal squid is the largest invertebrate on Earth by mass. Yet for decades, scientists knew it primarily through fragments recovered from the stomachs of sperm whales. Massive beaks hinted at an animal of extraordinary proportions, while the living creature itself remained unseen. Only during the year 2007 did researchers obtain photographs of a living adult, transforming a creature inferred largely from scattered remains into an observed inhabitant of the deep sea. These discoveries share a common thread. The deep ocean rarely surrenders its inhabitants willingly. Large animals with global distributions can persist for millions of years while remaining almost entirely beyond direct observation. Knowledge often arrives gradually, beginning with fragments, chance encounters, or indirect evidence, before advancing through improvements in technology capable of reaching environments previously inaccessible. None of these remarkable species provide evidence that Megalodon still survives. They do, however, illuminate something equally important about the ocean itself. They demonstrate that human understanding of the abyss remains incomplete, and that confidence regarding what does or does not inhabit its greatest depths must always be measured against the extraordinary size of the environment and the comparatively small portion that has ever been observed with our own eyes. A mystery becomes meaningful only after every ordinary explanation has been given its proper place. The unknown is not strengthened by ignoring inconvenient evidence. It becomes stronger only after surviving careful examination. With that principle in mind, the remaining possibility of Megalodon surviving into the present must now stand before the most formidable biological arguments ever assembled against it. These arguments deserve careful attention because they arise not from speculation, but from decades of observation across marine biology, paleontology, ecology, and oceanography. The first challenge is simply one of scale. Current research suggests that a fully grown megalodon may have reached approximately 24.3 kilometers, that is, nearly 15.1 miles. That figure is obviously impossible for a shark, revealing the importance of interpreting measurements correctly. The accepted estimate is approximately 24.3 meters, which is about 80 feet, placing the animal among the largest predators ever known. Creatures of such extraordinary size rarely pass unnoticed. Large whales leave scars on ships, become entangled in fishing equipment, generate unmistakable acoustic signatures, and occasionally wash ashore after death. If a breeding population of animals this immense still occupied the modern ocean, it would almost certainly produce traces extending far beyond isolated stories or uncertain observations. Its own physiology presents an equally serious obstacle. Earlier, evidence established that Megalodon maintained a body temperature approximately 7 degrees Celsius or 45 degrees Fahrenheit above the surrounding seawater through regional endothermy. That adaptation provided enormous advantages, while the oceans remained warm and productive, allowing sustained activity across broad ranges. Yet the same adaptation becomes costly within the abyss. Water near the deepest ocean floor approaches temperatures only slightly above freezing. Maintaining such a large body at a substantially warmer temperature would require an extraordinary and continuous expenditure of energy. The very adaptation that once strengthened the species becomes difficult to reconcile with permanent life in such cold surroundings. That energetic burden leads directly to the question of food. The abyss is vast, yet it is not especially rich. Far below approximately 1,000 meters, that is nearly 3,281 feet, sunlight never reaches the water, and the supply of energy entering the ecosystem becomes severely limited. Large animals certainly exist there, but they are scattered across enormous distances. The caloric demands previously estimated for Megalodon require a dependable supply of substantial prey. Sparse deep-sea megafauna simply do not appear capable of supporting a stable population of predators, requiring such immense daily energy intake. The arithmetic grows increasingly difficult the more closely it is examined. Reproduction presents another biological barrier. Fossil evidence consistently indicates that juvenile Megalodon developed within protected coastal nursery environments where shallow water, abundant food, and relative safety increased survival during the earliest stages of life. Those habitats were products of ancient oceans shaped by climatic conditions very different from those existing today. Comparable nursery systems have not been identified within the deep sea. Even if a few adults somehow endured in remote regions, sustaining a healthy breeding population without appropriate juvenile habitat becomes extraordinarily improbable across many generations. The record preserved by living whales strengthens this conclusion further. Modern sperm whales routinely descend to approximately 2 kilometers, which is about 1.2 miles, and sometimes even deeper, while searching for prey. Their powerful biological sonar constructs detailed acoustic information about the environments they traverse. Individuals examined by marine researchers often bear scars from encounters with giant squid, rival whales, and other hazards of the deep. Yet despite extensive study, no confirmed sperm whale has displayed injuries, bite patterns, or acoustic evidence consistent with attacks from an animal possessing the jaw geometry and immense dentition reconstructed for Megalodon. Taken together, these constraints form a remarkably coherent picture. None of them alone absolutely eliminates every imaginable possibility of survival. Collectively, however, they narrow that possibility into an exceptionally small space. The uncertainty explored within the previous passages remains genuine, yet it exists alongside biological realities that are equally genuine. Any modern survival hypothesis must therefore explain not only where such an animal could remain unseen, but also how it could overcome every one of these formidable ecological limits at the same time. Nature occasionally preserves an answer that resembles a contradiction. After examining the formidable biological barriers facing any surviving population of Megalodon, it becomes equally important to recognize that the deep ocean has already revealed at least one shark whose existence challenged long-held expectations. It does not dissolve the arguments presented before. Instead, it reminds us that life beneath the surface sometimes follows rules that appear unfamiliar until careful observation finally uncovers them. Among the most remarkable examples is the Greenland shark, a predator inhabiting some of the coldest marine environments on Earth. It is regularly encountered at depths exceeding 2,000 meters, which is about 6,562 feet, where the surrounding water hovers near 0 degrees Celsius, or 32 degrees Fahrenheit. These conditions would seem inhospitable to many large marine animals, yet the Greenland shark has evolved to move through this realm with remarkable efficiency, occupying an ecological niche that remained poorly understood for generations. Although considerably smaller than Megalodon, the Greenland shark still reaches extraordinary dimensions. Individuals may grow to approximately 7 meters, which is about 23 feet, making them among the largest living predatory sharks. Even more astonishing than their size is their lifespan. Through carbon isotope analysis of proteins preserved within the lenses of their eyes, researchers have determined that some individuals have lived for more than 400 years. One widely studied specimen was estimated to be approximately 392 years old, meaning it first entered the ocean before the beginning of the 30 Years' War. A creature can therefore survive across centuries, while remaining almost entirely beyond ordinary human observation. The explanation lies not in unusual strength or speed, but in metabolism. Unlike Megalodon, the Greenland shark is not warm-blooded. Every aspect of its biology is adapted to conserving energy. Its movements are deliberate, its growth exceptionally slow, and its demand for food far lower than that of similarly sized predators inhabiting warmer seas. Rather than requiring frequent access to abundant prey, it can persist on infrequent feeding opportunities, scavenging when possible, and hunting when circumstances allow. In the nutrient-limited environment of the deep ocean, such efficiency becomes an extraordinary advantage rather than a weakness. That distinction is essential because it defines the boundary between precedent and proof. Nothing about the Greenland shark demonstrates that Megalodon could have adopted the same strategy. A warm-blooded predator measuring approximately 24 meters, which is about 79 feet, would possess an entirely different metabolic profile from a cold-adapted shark less than one-third that length. The amount of energy required to sustain body temperature, maintain muscle activity, and reproduce would remain vastly greater. The biological arithmetic discussed previously does not disappear simply because another shark has mastered deep water under very different conditions. Yet, the Greenland shark contributes something equally valuable to the discussion. It establishes that a large shark can inhabit cold, poorly explored depths while leaving remarkably little trace of its existence. For centuries, people living around northern waters knew of the animal, but science possessed only fragmentary knowledge of its biology. Even today, many aspects of its behavior, migration, reproduction, and population size remain uncertain because direct observation is extraordinarily difficult. The ocean has demonstrated that immense stretches of habitat can conceal even substantial vertebrate predators from continuous study. That lesson extends beyond any single species. The deep sea operates according to ecological rhythms, unlike those familiar near the surface. Encounters are rare, distances are immense, and opportunities for observation remain surprisingly limited despite modern technology. The Greenland shark stands as living evidence that invisibility within such an environment is not impossible. At the same time, its biology also illustrates why survival there depends upon adaptations profoundly different from those reconstructed for Megalodon. Rather than weakening the biological case against modern survival, this remarkable shark sharpens it by revealing precisely which evolutionary traits make enduring life in the abyss possible, and which traits would have made such a transition extraordinarily difficult. Some dates become so familiar that they begin to sound permanent, as though they were carved into stone rather than assembled from evidence. The extinction of Megalodon is often presented this way. Popular books, documentaries, and articles frequently repeat that the giant shark disappeared approximately 3.6 million years ago. The number is widely accepted because it represents the strongest conclusion supported by current research, yet it is still an estimate shaped by the fossil record available today. Like every scientific conclusion built upon incomplete evidence, it has changed before, and it may become more refined as new discoveries emerge. For many years, the prevailing view placed the disappearance of Megalodon near the boundary between the Pliocene and the Pleistocene, approximately 2.6 million years ago. That estimate arose from careful statistical work using a method known as optimal linear estimation. The approach attempts to calculate the probable end of a species by examining the pattern of its final fossil occurrences rather than assuming the youngest known fossil marks the exact moment of extinction. It was, and remains, a legitimate scientific technique when applied to suitable data. Then another careful examination reshaped the picture. During 2019, paleontologist Robert Boesenecker and fellow researchers assembled a densely sampled fossil record from the North Pacific while removing specimens considered unreliable because of uncertain geological context or questionable identification. After correcting those occurrence records and applying revised analyses, they concluded that the evidence favored an extinction approximately 3.6 million years ago, rather than 2.6 million years ago. The newer estimate gradually became the dominant interpretation because it rested upon a more carefully filtered collection of fossils. The difference between those conclusions deserves careful attention. They are separated not by a few centuries or even a few thousand years, but by roughly 1 million years. Both studies relied upon accepted scientific methodology. Both attempted to answer the same question. Both were conducted by researchers following established standards of paleontological analysis. Yet they produced substantially different answers because they worked from different data sets and different judgments about which fossil occurrences deserved confidence. That gap is itself a reminder that the fossil archive, while remarkably rich in Megalodon teeth, remains uneven across both geography and geological time. Occasionally, reports have appeared describing Megalodon teeth that seem younger still, extending into the Pleistocene. These specimens have attracted understandable attention because they would shorten the distance between the species and the modern world. Careful investigation, however, has usually revealed alternative explanations. Some teeth were transported from older sediments through the geological process known as reworking. Others came from deposits disturbed by natural forces or human activity, making their original position uncertain. In still other cases, the surrounding sediment could not be dated with sufficient confidence. For these reasons, the scientific community generally regards such claims as unreliable. Unreliable, however, is not identical to impossible. It means the available evidence does not currently satisfy the standard required for acceptance. The deeper challenge is structural rather than procedural. Establishing the final appearance of any extinct marine species requires a fossil record that is dense, consistently preserved, accurately dated, and distributed across many different ocean basins. Megalodon provides an extraordinary abundance of fossils overall, yet those fossils are concentrated unevenly in space and time. Vast stretches of ancient seafloor remain unsampled, while other regions preserve long intervals with few recoverable remains. Such gaps naturally widen the range of possible interpretations, even when researchers apply the most rigorous analytical tools available. For that reason, the date most often repeated today should be understood not as an immutable boundary, but as the strongest conclusion supported by present evidence. It represents disciplined scientific reasoning rather than unquestionable certainty. The uncertainty surrounding that conclusion does not point in only one direction. Future discoveries could strengthen the existing estimate, shift it slightly earlier, or move it modestly later. That measured uncertainty is not a weakness in science. It is one of the clearest signs that the evidence continues to guide the conclusion rather than the conclusion dictating the evidence. Evidence and mystery occupy different places within science, even though they are often spoken of together. After tracing the strongest biological arguments against the survival of Megalodon, it becomes equally important to separate confirmed observations from speculation with great care. No verified sonar contact, authenticated video recording, tissue sample, skeletal remain, or living specimen has ever demonstrated that Megalodon survives in the modern ocean. That statement reflects the present scientific consensus and forms the foundation upon which every further discussion must rest. Yet beneath that certainty lies another reality, one concerned not with proof of a giant shark, but with the practical limitations of observing the largest environment on Earth. Modern sonar systems are extraordinarily capable, but they are not perfect windows into the abyss. Sound waves bend through layers of differing temperature and salinity. Dense schools of fish can resemble solid structures. Vast blooms of gelatinous animals may appear larger than expected. Instrument interference, shifting currents, and complex reflections from underwater terrain all introduce ambiguity into acoustic data. As a result, deep ocean surveys routinely produce contacts that investigators cannot immediately identify with confidence. Oceanographers have documented such anomalous sonar returns for decades. Some appear as large moving objects that briefly emerge before fading from detection. Others travel in ways that initially seem inconsistent with known vessels or mapped terrain. In nearly every carefully studied case, the most probable explanations involve thermal layering, biological aggregations, unusual current structures, or technical artifacts generated by the equipment itself. Occasionally, however, the available information remains insufficient to determine exactly which explanation is correct. An unresolved sonar contact, therefore, represents incomplete information rather than evidence for an extraordinary animal. A similar lesson emerges from the history of undersea communication cables stretching across the seafloor. Since the earliest generations of telegraph cables and continuing through the era of modern internet infrastructure, operators have occasionally recovered damaged sections bearing tooth impressions or gouges attributed to large marine animals. Some bite patterns resemble those expected from known sharks. Others cannot be confidently assigned to any documented species because the marks lack enough distinguishing characteristics. Engineers have therefore accumulated records of unexplained biological damage occurring far below the surface, not as proof of an unknown predator, but as reminders that interactions in deep water are often difficult to observe directly. Marine forensic investigations occasionally encounter comparable uncertainty when examining whale carcasses drifting through remote parts of the ocean. Many wounds can be matched confidently to familiar scavengers or predators. Others display bite arrangements that resist straightforward identification because decomposition, scavenging by multiple species, or incomplete preservation obscures the original pattern. Such cases are not surprising within an environment where scientists continue describing thousands of previously unknown marine organisms across the passing years. An unidentified bite mark is evidence that an interaction occurred. It is not evidence that a prehistoric shark produced it. Viewed together, these observations reveal something subtle but important about scientific exploration. The deep ocean regularly generates phenomena that investigators cannot explain immediately. Unresolved sonar echoes, uncertain bite impressions, and ambiguous traces do not occupy the same category as verified biological discoveries. They remain questions awaiting better information rather than conclusions waiting for confirmation. Responsible science preserves that distinction because extraordinary claims require evidence capable of surviving careful examination from every direction. That perspective ultimately strengthens rather than weakens the discussion. Acknowledging unexplained observations does not require abandoning established evidence, nor does accepting the extinction case require pretending that every deep ocean mystery has already been solved. Both ideas can exist comfortably together. The modern ocean continues to produce puzzles that challenge instruments, investigators, and interpretation alike. Those puzzles do not indicate that Megalodon survives beneath the waves. They demonstrate instead that unexplained observations are a natural consequence of studying an immense environment where direct observation remains remarkably limited and where the distance between uncertainty and evidence must always be crossed with patience rather than assumption. There is a difference between the question that captures public imagination and the question that occupies scientific thought. Conversations about Megalodon often settle into a simple choice. Either the giant shark survives somewhere beyond our sight, or it vanished forever millions of years ago. Such a framing feels satisfying because it promises a single definitive answer. Nature, however, rarely arranges its evidence into such convenient boundaries, especially within an environment as vast and difficult to examine as the deep ocean. Marine scientists generally approach the problem from another direction. Rather than asking whether Megalodon is alive, they ask what evidence would be necessary to establish its extinction, with the same degree of confidence applied to animals that inhabited forests, plains, or river valleys. Land preserves footprints, skeletons, nests, and layers of sediment that often remain accessible across enormous spans of time. The ocean behaves differently. Water moves. Sediments shift. Organisms consume one another, and geological processes continually reshape the archive beneath the waves. The standards for confidence, therefore, become more difficult to satisfy, even when the prevailing conclusion remains unchanged. That distinction explains why discussions surrounding extinction can appear more complicated than expected. The present scientific consensus continues to hold that Megalodon disappeared during the Pliocene. Fossil teeth, changing ocean conditions, declining prey availability, ecological restructuring, and the absence of convincing modern evidence all point strongly toward that conclusion. None of those lines of evidence has collapsed under careful examination. Together, they form a coherent explanation supported by decades of paleontological and marine research. At the same time, confidence is not identical to certainty. Scientists routinely evaluate the strength of conclusions according to the quality and completeness of available evidence. When studying animals that once walked across exposed landscapes, confidence can approach extraordinary levels because many different forms of evidence converge upon the same answer. A marine predator that spent nearly its entire existence within deep water presents a fundamentally different challenge. The environment itself removes, buries, redistributes, and conceals evidence in ways that have no close parallel on land. This distinction is not a weakness in scientific reasoning. It is one of its defining strengths. Science separates what evidence strongly supports from what evidence absolutely proves. Those categories overlap frequently, but they are not interchangeable. For Megalodon, the fossil record provides compelling support for extinction. The deep ocean, however, remains so incompletely explored that it also limits the certainty with which any claim about total absence can be expressed. These ideas do not oppose one another. They describe different aspects of the same problem. Confusion often arises when consensus and certainty are treated as though they mean exactly the same thing. Consensus reflects the conclusion that best explains the evidence presently available. Certainty would require demonstrating that no alternative remains possible within the limits of observation. In an environment where humanity has visually examined less than a tiny fraction of the seafloor, those standards naturally diverge. The scientific community, therefore, maintains confidence in extinction while also recognizing that the ocean itself imposes unavoidable limits upon what any investigation can establish beyond all conceivable doubt. Holding those two thoughts together requires patience rather than contradiction. The fossil evidence accumulated across millions of years remains persuasive and deserves the weight it carries. The extraordinary scale and complexity of the deep ocean deserve equal respect because they define the boundaries within which that evidence must be interpreted. neither consideration cancels the other. Instead, they combine into a more complete understanding of how scientific knowledge grows, not through absolute declarations, but through conclusions that become stronger as evidence accumulates. While remaining open to revision, should genuinely compelling new evidence ever emerge from the immense waters that still lie beyond direct human observation. Extinction leaves different kinds of footprints depending upon where life unfolds. Across broad plains or ancient forests, the passing of a great animal often lingers in scattered bones, preserved tracks, or layers of earth that capture a long history of changing ecosystems. The sea tells its stories another way. Its currents erase, its chemistry transforms, and its immense depth conceals far more than it reveals, allowing countless lives to disappear with scarcely a visible mark. Every creature that dies in the open ocean begins a journey unlike any found on land. Soft tissues are quickly consumed by scavengers and microscopic life. Skeletons descend through an endless column of water, where pressure, chemistry, and time reshape what remains. Sharks present an even greater challenge because their bodies are composed primarily of cartilage rather than dense bone. Cartilage decays rapidly, leaving little opportunity for preservation. Only under uncommon geological conditions does any portion of such an animal become part of the fossil record. Most vanish completely, leaving behind nothing except the rare, durable structures capable of surviving immense spans of time, such as teeth. Because of this, the ocean rarely offers a complete archive of the creatures that once inhabited it. Fossilization requires an unusual combination of rapid burial, favorable sediment, chemical stability, and extraordinary luck. Countless marine organisms lived, hunted, reproduced, and died without leaving any recognizable trace for future generations. The absence of remains therefore carries a different meaning beneath the waves than it often does upon land. It reflects not only biological history, but also the remarkable difficulty of preserving evidence within a constantly changing environment. Even modern extinctions demonstrate how elusive disappearance can become in aquatic habitats. The baiji, also known as the Yangtze River dolphin, inhabited one of the most intensively studied river systems on Earth. Researchers observed the species for decades, documented its decline, and eventually organized extensive surveys across its remaining habitat. When those expeditions failed to locate surviving individuals, the species was declared functionally extinct. Yet debate continued for years afterward because proving complete absence, even within a single river under sustained observation, proved more difficult than many expected. A similar lesson emerged from the history of the oceanic white-tip shark. Early explorers described this predator as astonishingly common across tropical seas, so widespread that encounters seemed almost routine. Within a single human lifetime, relentless fishing pressure reduced its population by well over 95% across much of its range. The decline unfolded largely beyond public attention, hidden within an ocean too vast for constant observation. A transformation of extraordinary magnitude occurred without dramatic scenes upon the surface, illustrating how profoundly marine ecosystems can change while remaining almost invisible to everyday experience. These examples reveal a broader truth about extinction in aquatic environments. Even species that scientists know well, actively monitor, and search for within comparatively accessible waters can fade toward disappearance without producing unmistakable evidence at every stage. The challenge becomes even greater for animals associated with remote depths, scattered populations, or habitats visited only occasionally by research expeditions. In such settings, the line between presence, rarity, and extinction becomes increasingly difficult to define with absolute certainty. This perspective does not weaken the evidence surrounding Megalodon. Its disappearance from the fossil record remains one of the strongest observations supporting extinction, and that absence deserves serious scientific weight. At the same time, the fossil record represents only a narrow window through which the immense history of marine life can be viewed. It illuminates many chapters while leaving others in shadow, shaped as much by the conditions of preservation as by the animals themselves. Seen in this light, extinction within the ocean is seldom a single dramatic event preserved for all time. More often it resembles the gradual fading of a distant signal, discerned through scattered fragments, careful comparison, and patient interpretation. The sea keeps many of its histories incomplete, reminding us that understanding its past depends not only upon what has endured, but also upon recognizing how much has been carried beyond the reach of lasting evidence. A shoreline can appear to offer gifts from the present, even when every object upon the sand carries a story that began in an ocean long vanished. Among shells, polished stones, and fragments shaped by waves, another discovery continues to draw people back to the same stretches of coast year after year. Megalodon teeth still emerge from beaches across the world with remarkable regularity, not as extraordinary accidents, but as expected finds in places where ancient marine sediments are steadily revealed by the patient work of water and time. Some coastlines have become especially well known for these discoveries. Ancient marine deposits exposed along rivers and coastal plains in North Carolina, South Carolina, Florida, and Maryland in the United States yield abundant specimens. Rich phosphate sediments in Morocco have produced countless examples, while fossil-bearing coastal deposits in Belgium, Australia, and Japan continue to contribute their own remarkable collection. These locations share a common history. Millions of years ago, each rested beneath seas that supported thriving marine ecosystems where Megalodon lived, hunted, and shed teeth throughout its lifetime. The journey from buried fossil to modern beach follows a consistent, natural process. River channels gradually carve through ancient sediment layers. Waves wear away coastal cliffs, grain by grain. Dredging occasionally uncovers deposits that have remained untouched since distant geological ages. As these layers erode, fossilized teeth are released from the rock that enclosed them. Ocean currents and tides then carry many of them across the seafloor before depositing them upon beaches, riverbanks, or shallow coastal waters where collectors eventually encounter them. One of the most productive examples lies along the Calvert Cliffs in Maryland. There, erosion beside the Chesapeake Bay continuously exposes marine sediments dating back to the Miocene epoch. Thousands of Megalodon teeth are recovered from this region each year, each one preserving the unmistakable form of an apex predator that disappeared millions of years ago. Despite their abundance, none display the characteristics expected from recently shed teeth. Their appearance reflects immense geological age rather than recent biological activity. The colors of these fossils tell the same story. Fresh shark teeth are naturally pale, protected by smooth enamel formed within a living animal. Megalodon teeth, found on beaches, instead display deep shades of brown, gray, black, and sometimes blue-green. These colors developed gradually as minerals within surrounding sediments replaced or stained portions of the original material over immense spans of time. Local chemistry determines the final appearance, allowing teeth from different fossil beds to display distinct colors while remaining equally ancient. By the time they reach the shoreline, they have become geological objects as much as biological remains. This distinction is essential when interpreting new discoveries. Finding a megalodon tooth today does not indicate that a living shark recently passed through nearby waters. It indicates that an ancient sediment layer has only recently surrendered one of its preserved fossils. The tooth records the existence of an animal that lived millions of years before the coastline assumed its present form. It functions as a messenger carried forward through geological processes rather than as evidence of a surviving population. Yet there remains something deeply remarkable about holding one of these fossils in an open hand. The serrated edges often remain crisp enough to catch the light. The curves of the crown retain the same elegant geometry that once sliced through flesh beneath prehistoric seas. After perhaps 15 million years beneath layers of sediment, the structure still reflects the design of the living animal with astonishing fidelity. Time has transformed its chemistry without erasing its identity. Each newly uncovered tooth, therefore, speaks less about the present ocean than about the extraordinary endurance of the past. The sea buries its history with immense patience, preserving certain fragments while allowing countless others to disappear forever. Then, according to rhythms measured in erosion rather than memory, it returns those fragments to daylight. A beachcomber stoops to lift what appears to be a simple fossil, yet the object has completed a journey across millions of years before resting for a brief moment upon the shore once again. Sometimes the strongest evidence for a vanished animal is not found in stone or preserved within sediment, but in the living world that continued after its departure. Ecosystems remember their former inhabitants in subtle ways. Predators shape the behavior, abundance, and evolution of the species around them, and when one of those dominant hunters disappears, the effects ripple outward across countless generations. The ocean still bears those lingering signatures, written not as monuments to Megalodon itself, but as changes that unfolded after its long reign had ended. The period surrounding Megalodon's disappearance marked a broader transformation within the seas. During the late Pliocene marine megafauna extinction event, numerous large marine species declined or vanished as climates cooled, coastlines shifted, and food webs reorganized. Megalodon disappeared within this interval, yet it was only one participant in a much larger ecological transition. The marine world emerging afterward was recognizably different from the one that had existed for the previous 20 million years, with new balances gradually replacing older ones. Among the most intriguing changes involved the great baleen whales. Fossil evidence indicates that both their diversity and the distribution of their body sizes shifted during the millions of years following Megalodon's extinction. Several researchers have suggested that the disappearance of such an enormous apex predator reduced one of the greatest selective pressures acting upon these whales. Freed from constant predation by an animal capable of attacking even very large individuals, whale populations may have expanded in both abundance and average size across succeeding ages. This possibility offers an elegant ecological interpretation rather than a complete explanation. Modern blue whales, fin whales, and humpback whales almost certainly owe their extraordinary dimensions to many interacting forces, including climate, food availability, migration, and evolutionary competition. Yet the removal of an immense predator from the ecosystem may have created ecological space that no remaining hunter could fully occupy. Without that persistent pressure, natural selection could favor increasingly larger whales whose size offered advantages unrelated to escaping Megalodon itself. Behavior may preserve even older echoes than anatomy. Many baleen whale species undertake immense migrations between feeding grounds and breeding areas, crossing entire ocean basins every year. Some of these journeys appear surprisingly long when measured only against present-day distributions of food and suitable calving habitat. Evolutionary biologists have proposed that certain migration routes may represent inherited behavioral strategies shaped by ancient predation risks. Even after the original danger disappears, successful behaviors can persist because natural selection tends to preserve what already works. Across countless generations, instinct may continue guiding animals along paths first established under ecological conditions that no longer exist. Whether this particular explanation proves correct in every detail, it illustrates an important principle. Evolution does not erase its earlier chapters simply because the environment changes. Adaptations often outlive the circumstances that produce them, remaining embedded within populations long after the original selective force has vanished. The living ocean, therefore, carries memories extending far beyond recorded history, expressed through movement, behavior, and relationships among species, rather than through conscious recollection. The structure of today's community of large marine predators also reflects this transformation. Instead of a single, overwhelming hunter dominating the upper levels of the food web, ecological influence is distributed among several remarkable species. Great white sharks, killer whales, and sperm whales each occupy powerful but distinct roles shaped by different hunting strategies, habitats, and physiological adaptations. None individually approaches the combination of size and ecological reach inferred for Megalodon. Rather than one supreme predator, the modern ocean is governed by a balance among several specialized hunters. Viewed from this perspective, Megalodon's extinction was not simply the ending of one extraordinary lineage. It became an event that altered the architecture of marine ecosystems across millions of years. The whales crossing today's oceans, the predators that now share the highest levels of the food web, and the relationships connecting them all, exist within an ecological landscape shaped, in part, by the absence of the giant that once stood above them. The ghost of Megalodon endures, not as a hidden survivor beneath the waves, but as a lasting influence woven into the living fabric of the sea itself. An idea becomes most revealing when its requirements are laid out one beside another. Imagining that Megalodon survived into the present is not simply a matter of wondering whether a few individuals escaped extinction. It demands a complete biological scenario whose every component must function successfully across millions of years. The more clearly those conditions are defined, the more sharply the challenge comes into focus, not as fantasy, but as a rigorous exercise in ecological reasoning. Any surviving population would first need to overcome the mathematics of reproduction. A handful of isolated animals could not preserve a species indefinitely. Genetic diversity declines within populations that become too small, increasing the likelihood of harmful inherited traits and reducing resilience against environmental change. Population genetic studies of large, slow-reproducing vertebrates consistently indicate that a stable future requires at least several hundred breeding individuals under favorable conditions. A population much smaller than that would face steadily increasing biological pressure toward eventual disappearance. Those animals would also require an extraordinary and dependable source of food. Estimates of Megalodon's metabolism suggest that a single adult may have required roughly 100,000 kilocalories each day simply to sustain its immense body. Even a surviving population of 200 individuals would therefore consume prey equivalent to many tens of thousands of large marine mammals over the course of a single year. Such demand would impose a substantial ecological burden upon whatever ecosystem supported it, leaving little room for prolonged scarcity. Food alone would not solve the deeper physiological challenge. Fossil evidence indicates that Megalodon possessed adaptations associated with elevated internal body temperature, allowing powerful swimming and efficient hunting in comparatively warm waters. Maintaining such physiology within the near-freezing depths of much of the abyss would impose immense energetic costs. Survival would therefore likely require regular access to warmer deep water, perhaps within equatorial regions where temperature gradients remain less extreme than those found beneath polar seas. Even there, balancing heat production against available food would remain a demanding biological equation. Reproduction presents another formidable obstacle. Evidence from the fossil record indicates that juvenile megalodons developed within shallow coastal nursery habitats, rich in food and comparatively sheltered from larger predators. No known large shark has abandoned such a strategy in favor of an entirely deep-water reproductive system while retaining comparable body size and ecological role. For a surviving population to persist, it would either have needed to evolve a completely different method of reproduction without leaving any fossil or observational evidence, or continue using coastal nurseries located in places that have somehow remained entirely beyond human detection. Each of these requirements already represents a considerable challenge when considered independently. Together, they become increasingly difficult to reconcile. A viable population must remain genetically healthy. It must secure an immense and reliable food supply. It must inhabit waters compatible with its physiology. It must reproduce successfully through a strategy unlike any documented among comparable sharks, or conceal traditional nursery grounds across geological time without generating convincing evidence of their existence. Evolution undoubtedly possesses remarkable creative power. Across millions of years, it has produced extraordinary adaptations that once seemed unimaginable. Yet evolutionary change remains constrained by inherited anatomy, environmental pressures, and ecological opportunity. Transforming an enormous coastal apex predator into an animal capable of surviving almost entirely beyond observation, while simultaneously solving every challenge of metabolism, reproduction, and food availability, would require an exceptional sequence of successful adaptations. Such a transformation is not forbidden by natural law, but neither is it anticipated by the broader patterns repeatedly observed throughout evolutionary biology. For this reason, the biological case stands among the strongest arguments against modern survival. The possibility cannot be dismissed merely because it appears unlikely, yet neither can likelihood be separated from evidence. The deeper the requirements are examined, the narrower the path becomes. By the time every ecological, physiological, and reproductive condition is placed together, the remaining space in which a surviving population could exist has become extraordinarily small, defined not by imagination alone, but by the demanding arithmetic of life itself. Knowledge is often measured not only by what has been discovered, but also by the boundaries beyond which discovery has not yet reached. The discussion surrounding Megalodon rests upon one of those boundaries, where the language of science becomes especially careful. Philosophers of science have long distinguished between the absence of evidence and evidence of absence. The difference appears subtle, yet it shapes how every conclusion is weighed, especially when the subject lies far beyond ordinary observation. The absence of evidence is the easier idea to understand. Despite generations of marine exploration, no verified modern megalodon tooth has been recovered from living tissue or recent sediment. No authenticated photograph has revealed such an animal. No complete carcass has drifted into view. No confirmed biological sample has matched its identity. No sonar contact has survived careful examination as convincing proof. Each missing piece matters. Together, they form a substantial body of negative evidence, accumulated across decades of research by countless expeditions operating in oceans around the world. Evidence of absence carries a different meaning. It suggests that searching has become sufficiently complete that continued failure to detect a species becomes positive evidence that the species no longer exists. This is the position held by the overwhelming scientific consensus regarding Megalodon. It is not based upon a single missing fossil or one unsuccessful expedition. Instead, it emerges from many independent observations, including the fossil record, marine ecology, evolutionary biology, physiology, oceanography, and the continued absence of any verified encounter despite increasingly sophisticated technology. Yet, this conclusion depends upon an assumption whose strength deserves careful examination. Evidence of absence becomes persuasive only when the search itself approaches completeness. On land, that standard can often be approached. Forests, deserts, mountains, and plains may be surveyed repeatedly from the ground, from the air, and from satellites. Large animals leave footprints, skeletons, nests, droppings, and many other traces. Even elusive species eventually reveal themselves through accumulated signs. The deep ocean follows different rules. Most of its volume remains beyond direct observation. Immense regions have never been examined except through brief passes of instruments descending for specific missions. A vast water column separates the surface from the seabed, while darkness, pressure, and distance limit every method of exploration. Even today, much of what scientists understand about those depths comes from scattered observations collected across enormous expanses rather than continuous monitoring. The search is extensive, yet it cannot honestly be described as comprehensive in the same way that extensive surveys on land sometimes can. Recognizing this limitation does not overturn the existing consensus. The most reasonable interpretation of all available evidence remains that Megalodon became extinct millions of years ago. Every major line of investigation points toward that conclusion, and none has produced verified evidence demanding its revision. Scientific understanding advances by following the strongest available evidence rather than waiting for perfect certainty, because perfect certainty is rarely attainable in any field of inquiry. The distinction becomes clearer when compared with an animal such as the woolly mammoth. Its former habitat has been explored across vast northern landscapes. Complete skeletons have been recovered. Preserved soft tissues have yielded genetic material detailed enough to reconstruct nearly the entire genome. Multiple independent records converge upon the same historical conclusion. Confidence grows because the evidence is abundant, varied, and repeatedly confirmed through different methods. The ocean offers no equivalent archive for many of its vanished inhabitants. Cartilage seldom survives long enough to fossilize. Organic remains disappear into environments that recycle biological material with remarkable efficiency. What reaches the fossil record represents only a fraction of what once lived. Science, therefore, reaches its conclusions using incomplete evidence, while remaining fully aware that incompleteness itself is part of the environment being studied. In that sense, the modern verdict concerning Megalodon reflects both confidence and humility. Confidence comes from the remarkable agreement among diverse scientific disciplines. Humility comes from recognizing that the conclusion concerns a realm where evidence is unusually difficult to preserve, unusually difficult to recover, and permanently shaped by the immense hidden spaces of the deep ocean. There comes a point in every exploration when the landscape itself becomes the central character. The deep ocean reaches that point almost immediately. It is not an empty interval stretching between the familiar surface and the seabed below. It is the largest habitable environment on Earth when measured by volume, containing about 1,335,000,000 cubic kilometers of water, which is about 829 million cubic miles. More than 95% of that immense volume exists beneath permanent darkness, beneath crushing pressure, and beyond the reach of ordinary light-based observation. Its scale alone changes the meaning of discovery. Every continent, every desert, every mountain range, and every forest occupies only a fraction of the living space contained within the global ocean. Yet, despite covering most of the planet and enclosing the greatest habitat ever known, it remains the least understood major environment in the natural world. Vast stretches have never been sampled directly. Many have been crossed only by passing instruments or distant acoustic surveys. Countless regions remain known more through inference than observation. Life has answered this extraordinary environment with forms unlike those found anywhere else. Where sunlight cannot penetrate, vision often surrenders its familiar role, replaced by senses adapted to pressure, vibration, and chemistry. Bioluminescence becomes the language of countless inhabitants, producing living signals that flash, shimmer, or pulse through the darkness. Around hydrothermal vents, entire communities draw their energy not from sunlight, but from chemosynthesis, transforming chemicals rising from Earth's interior into the foundation of thriving ecosystems. Bodies stretch into improbable shapes, bones become lighter or disappear altogether, and organs evolve according to rules written by depth rather than daylight. Each year, science formally recognizes roughly 2,000 new species, with many emerging from marine environments. Every accepted description expands a catalog that remains remarkably incomplete. After a decade of coordinated international research, the Census of Marine Life, involving about 2,700 scientists from 80 nations, concluded that somewhere between 700,000 and 1 million species likely inhabit the ocean. Fewer than 1/3 have been formally described. Even these estimates carry uncertainty because every expedition uncovers organisms that reshape expectations of where life can exist and how diverse it can become. The difficulty lies not in a lack of curiosity, but in the character of the environment itself. Pressure increases relentlessly with depth, compressing ordinary equipment until metal bends and delicate electronics fail. Darkness defeats cameras that depend upon reflected light. Communication with distant instruments becomes slower and more uncertain as they descend farther from the surface. Every mission demands specialized engineering, careful planning, and enormous expense simply to spend a brief period within an environment that has remained unchanged for millions of years. Even if technology continues advancing at its present pace, comprehensive exploration remains a task measured not in years but across many generations. The sheer volume of water, the complexity of the seabed, and the countless habitats suspended between them ensure that complete observation cannot be hurried. Every successful voyage illuminates only a minute fraction of an environment whose scale continually exceeds human intuition. Seen in that light, the deep ocean becomes something more than an unexplored destination. It is a scientific reality that resists certainty by its very nature. This does not weaken conclusions supported by strong evidence, nor does it strengthen extraordinary claims lacking proof. Instead, it reminds us that confidence and humility can exist together. Every statement about what the ocean contains and every statement about what it does not contain must ultimately pass through the same immense hidden world, a world whose greatest lesson may simply be that its true dimensions are far larger than the boundaries of our present understanding. Discovery often arrives without fanfare. A research vessel follows its planned course. Instruments descend into water that has never been examined in detail, and the familiar map of life expands once again. The ocean does not announce that something remarkable is waiting below. It simply keeps its inhabitants until observation, persistence, and a measure of fortune happen to arrive at the same place and the same moment. During the year 2022, researchers surveying a remote seamount near Morocco encountered something wholly unexpected. Beneath the surface, they documented a deep-sea coral reef that was still actively growing, the only living reef of its kind then known within the entire Mediterranean Sea. The discovery did not result from an extraordinary change in the environment. The reef had almost certainly existed for centuries. It remained unknown because the surrounding seafloor had never been examined with sufficient detail. An entire living ecosystem had occupied its place beyond human awareness simply because no expedition had previously looked there. A similar story unfolded several years earlier near Jarvis Island in the Central Pacific Ocean. During the year 2019, a remotely operated vehicle descended through deep water, recording organisms as it traveled. Among the images returned was an unfamiliar shape that marine biologists could not immediately identify. Careful examination later confirmed the animal as a goblin shark. The species itself was already known through scattered encounters and preserved specimens, yet this marked the first time it had ever been filmed alive within its natural deep-water habitat. The shark had not suddenly appeared. Human observation had finally reached the place where it already lived, roughly 2 kilometers below the surface, which is about 1.2 miles. Another inhabitant of the deep illustrates the same lesson with remarkable clarity. The Magnapinna squid possesses an unusually small body suspended beneath extraordinarily long arms that may extend as much as 6 meters, which is about 20 feet. For many years, only a handful of confirmed encounters existed anywhere in the world. It seemed almost impossibly rare. Then, during the year 2020, a single survey of the Great Australian Bight documented 5 separate sightings. The animals had not multiplied overnight. Researchers had simply explored waters that had never before received systematic scientific attention. Even familiar predators continue to reshape scientific maps through discoveries of this kind. During the year 2024, the known range of the Pacific sleeper shark expanded into the South China Sea. Nothing suggests the species had recently migrated there. Instead, evidence indicated that the shark had occupied those waters long before scientists documented its presence. Geography changed only within human understanding, while the animal continued following patterns established far beyond recorded history. These examples are not extraordinary exceptions gathered from isolated centuries of exploration. They belong to a continuing pattern repeated throughout modern marine science. As remotely operated vehicles become more capable, as cameras endure greater depths, and as expeditions reach regions previously left unexplored, significant discoveries continue to emerge with remarkable consistency. Some involve organisms entirely new to science. Others reveal familiar species living in places or behaving in ways never before observed. Each expedition adds another thread to a tapestry that remains unfinished. This continuing record does not imply that every mystery conceals an undiscovered giant, nor does it weaken conclusions supported by extensive evidence. Instead, it reveals something more fundamental about the deep ocean itself. Its capacity to conceal life has always been proportional to the effort devoted to searching it. Every improvement in technology widens the circle of observation, yet that expanding circle remains surrounded by an immense frontier that has scarcely been examined. Against the total volume of the deep ocean, humanity has only begun the long process of learning the names of the creatures that have always been there, waiting beyond the edges of our maps. Some spans of time resist ordinary understanding. They can be written on a page, spoken in a sentence, or plotted across a chart, yet the mind struggles to contain them. The history of Megalodon belongs to that category. Its reign as the dominant predator of the world's oceans endured for approximately 20 million years, a span so immense that comparison becomes the only way to glimpse its true scale. Modern humans, known scientifically as Homo sapiens, have existed as a distinct species for roughly 300,000 years. Every story our species has ever lived, from the earliest communities to the present moment, occupies only a small fraction of the interval during which Megalodon hunted the seas. Its tenure at the summit of the marine food web lasted about 66 times longer than the entire existence of humanity. The oceans knew this predator for ages before the first human voice was ever spoken. The comparison grows even more striking when measured against recorded history. The first systems of writing appeared only about 5,000 years ago. Within that comparatively brief chapter unfolded every kingdom, every empire, every migration, every voyage across unknown waters, every philosophical tradition, every work of literature, every scientific revolution, and every technological achievement that defines civilization today. Measured against Megalodon's history, the whole recorded experience of humanity could fit inside its reign roughly 4,000 times. Civilizations rose, transformed, and vanished in spans that, from the perspective of deep evolutionary time, would scarcely register. No known terrestrial predator maintained ecological dominance for anything approaching such a duration. Continents changed, climates shifted, and dominant carnivores appeared and disappeared as ecosystems reorganized around new conditions. The oceans followed their own rhythms. Yet, throughout those immense changes, Megalodon remained. Generation followed generation through epochs that witnessed coastlines advancing and retreating, mountain ranges rising, and entire marine communities evolving beneath its presence. Among living sharks, only a few lineages have persisted across similarly vast stretches of geological time, yet they achieved that endurance through profoundly different strategies. The whale shark and the basking shark survive by filtering immense quantities of tiny organisms from the water rather than pursuing large prey. Their demands upon the ecosystem remain comparatively modest, allowing them to occupy stable ecological roles over millions of years. Megalodon existed at the opposite end of that spectrum. As an apex predator, its continued survival depended upon abundant populations of large animals capable of sustaining extraordinary energetic requirements. Remaining at the summit of the food web for 20 million years required not merely physical size, but remarkable ecological stability across changing oceans. Its influence reached far beyond its own survival. Every large marine mammal evolving during those millions of years did so beneath the persistent pressure of one overwhelming hunter. Body size, migration, reproductive behavior, and patterns of habitat use were shaped by ecosystems in which Megalodon represented a constant evolutionary force. The predator itself rarely appears in the fossil record beyond scattered teeth and occasional vertebrae, yet the responses of countless other species became part of its enduring legacy. Those teeth now emerge from sediments on nearly every continent, carried to the surface through erosion after remaining buried for millions of years. Each fossil is a durable fragment of an animal whose ecological influence extended far beyond the hard structures preserved in stone. The fossil record captures pieces of its anatomy, but it cannot fully preserve the living presence that once organized entire marine ecosystems across the globe. When extinction finally came, the change extended beyond the disappearance of a single species. The oceans lost a force that had structured their largest food webs for a span of time almost beyond imagination. What followed was not merely the absence of a predator, but the disappearance of an organizing principle that had endured through millions upon millions of years, leaving behind an ocean that still carries the shape of what was once there. By this point, the ancient shark itself has almost faded into the background, leaving behind a larger subject that has been present from the beginning. The real conversation has never belonged entirely to a single extinct predator. It belongs to the meeting place between human knowledge and the deepest waters of the planet, between what evidence allows us to say with confidence and the immense environment in which that evidence must be gathered. Across the history of science, confidence has always depended upon the character of the landscape being examined. The extinction of the woolly mammoth, the saber-toothed cat, the dodo, and the thylacine rests upon evidence collected in places where large-scale searches are physically achievable. Their bones remained on land, preserved in caves, frozen ground, dry sediments, or museum collections. Entire skeletons could be recovered, compared, and studied. Their former habitats became increasingly familiar through generations of observation until continued absence carried genuine scientific weight. In those environments, the disappearance of a large animal eventually became something that could be demonstrated rather than merely inferred. The story of Megalodon unfolded in a profoundly different setting. Its domain was not an open plain or an isolated island, but the greatest living environment on Earth, measured not by its surface but by its astonishing volume. That environment continues to challenge nearly every method available for direct observation. Pressure, darkness, immense distances, shifting currents, and the rarity of sustained exploration combine to limit what can be known through direct inspection. The question therefore asks science to establish the extinction of a giant apex predator within a habitat that remains, by every meaningful measure, only partially explored. None of this overturns the scientific conclusion. The fossil record provides compelling evidence that Megalodon disappeared millions of years ago, and the complete absence of verified modern specimens, fresh teeth, confirmed tissue, reliable imagery, or reproducible observations strongly supports that conclusion. The scientific consensus remains the most reasonable interpretation of everything presently available. Accepting that conclusion is entirely consistent with accepting the limitations imposed by the ocean itself. Those limitations simply shape the degree and character of scientific confidence. Confidence is never created in isolation. It grows from the quantity, quality, and completeness of evidence available for a particular question. The confidence appropriate for an extinct land animal whose habitat has been examined extensively is not constructed in exactly the same manner as confidence regarding a species that lived almost entirely within the deepest parts of the sea. The distinction lies not in the strength of the scientific method, but in the nature of the environment to which that method must be applied. As the years pass, every newly described deep water organism contributes something larger than its own discovery. Each unfamiliar fish, coral, crustacean, or cephalopod expands the known boundaries of marine life, while gently reminding researchers how much remains beyond present observation. Every expedition that returns with unexpected findings demonstrates both the remarkable power of modern exploration and the immense scale of what still lies outside its reach. Discovery and uncertainty continue to exist together, each defining the other with surprising harmony. Viewed from that perspective, the familiar question about Megalodon becomes less significant than the one resting beneath it. The enduring subject is not whether an ancient shark escaped extinction, but how certainty itself is earned within an environment that reveals its history only a fragment at a time. The deep ocean continues to answer with fossils, living species, geological records, and careful measurements, yet it does so according to its own pace. Science advances by listening patiently to those answers, recognizing both what has been established with confidence and what remains beyond the horizon of present knowledge. There are places on Earth where change is measured in seasons, where forests grow and fade within the span of a lifetime, and where mountains appear almost unchanged from one generation to the next. The ocean belongs to a different measure altogether. Its deepest reaches move according to clocks that count not years or centuries, but millions of years, carrying forward processes so gradual that they become almost invisible within the length of a human life. A megalodon tooth discovered upon a shoreline today begins its story in a world almost impossible to picture. It hardened beneath ancient seas during an age when the Sahara supported broad tropical forests instead of endless sand, when the Mediterranean basin had not yet assumed its present form, and when the Andes continued their long ascent toward the sky. Since that distant time, continents shifted, climates transformed, countless species appeared and disappeared, and human civilization eventually emerged for the briefest instant. Yet the tooth itself often reaches a collector's hand with serrated edges so crisp that it seems as though it entered the water only days before. The contrast is not an illusion. It is the consequence of geological preservation unfolding across spans of time that stretch far beyond ordinary imagination. The ocean does not preserve according to human schedules. It has no awareness of scientific expeditions, research funding, museum collections, or documentary narratives. Sediments accumulate grain by grain, currents alter their paths with extraordinary patience, and coastlines retreat through persistent erosion. Fossils remain concealed until those slow processes eventually uncover them. When an ancient tooth emerges from a riverbank or washes onto a beach, it does not announce a recent event. It marks the moment when geological history has finally reached a point where something hidden for millions of years can once again meet daylight. Far below the restless surface, another rhythm prevails. The abyss experiences none of the familiar cycles that shape life on land. Storms cannot disturb those immense depths. Seasonal winds never arrive. Sunlight never reaches the sea floor. Fine layers of sediment settle across vast plains with remarkable steadiness, covering objects so gradually that centuries pass without visible difference. In many places, what comes to rest within that landscape may remain protected for immense intervals before a shifting current, an underwater landslide, or the slow movement of the planet's crust alters its resting place. Geological time is not frozen there, but it proceeds with extraordinary restraint. The ocean itself has endured for approximately 3,800,000,000 years. Throughout that immense history, it has witnessed every chapter of Earth's biological story. It received the remains of creatures from each of the planet's 5 great mass extinctions. It collected volcanic ash, drifting sediments, microscopic shells, enormous skeletons, and the countless traces left behind by living organisms across uncounted ages. Almost all of that history still resides somewhere beneath the water, layered one chapter upon another, forming an archive whose greatest volumes remain unread because reaching them is so extraordinarily difficult. When fragments of that archive eventually return, they do so without urgency. A fossil exposed by a collapsing cliff, a shell lifted by dredging, or an ancient tooth revealed after persistent coastal erosion represents a conversation begun millions of years ago and answered only now. The ocean offers those fragments according to physical laws rather than human expectation. Nothing about the process is mysterious in the scientific sense. It follows the patient work of sedimentation, erosion, tectonic motion, and time itself. Yet there remains something profoundly humbling in recognizing that beneath the waves rests a history vastly older than memory, preserved with astonishing care, waiting through ages until the Earth itself decides that another page may finally be turned. After everything the evidence has revealed, after every fossil, every expedition, every biological calculation, and every careful distinction between what is known and what remains beyond direct observation, the answer settles into place with surprising simplicity. It is neither the certainty of legend nor the certainty of absolute finality. It is something narrower, stronger, and more faithful to the evidence itself. Megalodon is almost certainly extinct. That conclusion is supported by the most reliable geological record available. Fossils recovered from multiple ocean basins, examined across independent studies, and compared through successive generations of research, consistently indicate that confirmed Megalodon remains disappear from the record approximately 3,600,000 years ago. Since that time, no verified tooth formed by a living individual, no authenticated tissue, no confirmed carcass, and no scientifically validated observation has demonstrated that the species survived into the modern ocean. Taken together, these independent lines of evidence converge upon the same conclusion with remarkable consistency. The biological arguments strengthen that conclusion rather than weaken it. A predator of such extraordinary size would require an immense and dependable supply of food. Its energetic demands would be enormous throughout every stage of its life. It would also need access to water temperatures capable of supporting its physiology while maintaining suitable locations for reproduction and the protection of young animals. Modern whale populations show no verified pattern of injuries that would require the presence of such a predator, and no confirmed nursery habitat has ever been identified. None of these obstacles stands alone. Together they describe an ecological challenge of exceptional magnitude. Yet another truth remains equally important. The deep ocean continues to place firm limits upon what can be observed directly. Much of its volume has never been examined in detail. The fossil record itself, despite being one of the greatest achievements of Earth science, remains an incomplete archive shaped by preservation, burial, erosion, and discovery. Countless organisms lived without ever leaving fossils that survived into the present. Others remain hidden beneath sediments that may not be exposed for millions of years. Scientific understanding advances because new evidence continues to emerge, sometimes refining conclusions that once appeared complete. The history of Megalodon research illustrates this process. Estimates for the species' final appearance have become more precise as additional fossils were discovered and dating methods improved. That refinement did not overturn the conclusion of extinction, but it demonstrated something valuable about science itself. Conclusions are strengthened not by refusing revision, but by remaining open to better evidence whenever it appears. Confidence grows through continual testing rather than through permanent certainty. The most accurate position, therefore, avoids both extremes. It does not claim that Megalodon still inhabits the modern ocean because the available evidence strongly supports extinction. It also avoids claiming a degree of certainty that exceeds what the environment itself can provide. The deep ocean imposes structural limits upon observation, unlike those found in almost any terrestrial setting. Those limits do not invalidate the evidence. They simply define the boundaries within which scientific confidence is earned. Perhaps that conclusion lacks the dramatic certainty of a myth finally confirmed or finally destroyed. Even so, it reflects the discipline that has guided every careful investigation throughout this journey. The evidence points with compelling strength toward extinction, while the ocean continues to remind us that knowledge is always shaped by the world from which it is gathered. Holding both truths together is not uncertainty for its own sake. It is the most faithful expression of what the science presently supports, and the most honest answer we can offer. Long after the living animal disappeared from the world, its presence continues to arrive one fossil at a time. Teeth still emerge from riverbanks, coastal cliffs, and beaches where ancient sediments surrender fragments of a vanished sea. Countless others remain buried within layers of rock that have rested undisturbed for approximately 15 million years. Many more lie scattered across stretches of seafloor that no human expedition has yet reached, preserved beneath sediments that have patiently accumulated through ages beyond ordinary comprehension. The ocean that shaped Megalodon has never truly vanished. It has changed, certainly, as continents drifted, climates shifted, and generations of marine life rose and disappeared. Yet the living structure of today's seas still bears the imprint of that ancient predator. The immense baleen whales crossing entire ocean basins, the distribution of modern apex predators, and migration routes refined across immense spans of evolutionary history all belong to an ecosystem that was once organized around an animal whose influence endured for approximately 20 million years. That influence did not end in a single moment. It slowly became part of the biological inheritance of everything that remained. Seen from that perspective, the question has never been only about one extinct shark. It reaches toward something larger. It asks what it truly means for a species to be lost within an environment so vast that no complete inventory has ever existed. On land, disappearance can often be witnessed directly. Within the deep ocean, absence is filtered through distance, pressure, darkness, and extraordinary scale. The words lost and gone begin to carry different shades of meaning, not because evidence loses its value, but because the environment itself limits what evidence can reasonably reveal. Science continues along the only path it has ever followed, building conclusions from the strongest observations available while remaining prepared to revise them whenever stronger evidence appears. By that standard, the conclusion remains clear. Megalodon is almost certainly extinct. Every major line of geological and biological evidence supports that judgment. At the same time, the same body of scientific knowledge reminds us that only a minute fraction of the immense environment in which that conclusion must ultimately apply has been examined directly. These ideas do not compete with one another. Together, they define the remarkable challenge of understanding the deep ocean. Across geological time, the sea has preserved histories that no archive built by humanity could equal. It sheltered Megalodon through an age almost impossible to imagine, preserved its teeth with astonishing fidelity, and slowly returned those fossils to the surface through the patient work of erosion and shifting sediments. At the same time, it continues to shelter an extraordinary abundance of living organisms, many still unnamed, many still unseen, within habitats that remain beyond routine observation. Every new expedition broadens understanding, yet the horizon of the unknown remains immense. Whether Megalodon survives only in stone or only in memory, no longer feels like the largest truth waiting beneath the waves. The ocean itself endures. It remains older than civilization, larger than imagination, and governed by processes unfolding across spans of time that human lives can scarcely measure. It neither hurries to answer curiosity nor withholds its history out of mystery. It simply continues, revealing its story according to the patient rhythms of geology, evolution, and time. Perhaps that is the lasting gift of this journey, not certainty beyond all doubt, but an enduring respect for a world whose greatest depths still remind us that knowledge, like the sea itself, is always wider than the horizon we can presently see.